Hey everybody. Sorry I'm missing you today. We are going to get started in logarithms. We spent the last few days working on our exponentials. If you recall from the past when we looked at logarithms last semester, that logarithms and exponentials are just different ways of writing the same thing. Lots of benefits to rewriting exponentials as logarithms. There's a lot that we can do. So we're going to start with some basics and just how do we rewrite exponentials as logarithms, how do we rewrite logarithms as exponentials, and then I'm going to start to touch on the graphs of these as well. So on the board here I have y equals the log base b of x. Now if you recall, that's the same as, notice I have double arrows here, these are equivalent, you can switch back and forth between these two, they mean the same thing. B is the base of our logarithm, that's the base of our exponential. Okay. Y is the exponent. We have b to the y equals x. Y is our exponentials. Logarithms are the exponents. So we have b to the y equals x, equivalent. Let's switch back and forth between these two. So first one, let's rewrite this in logarithmic form. 5 to the 4th equals 625. So I'm starting with the exponential. I'm rewriting it as a logarithm. Okay, so I'll put log here. What's the base of my logarithm? Well, the base of the exponential is 5. Log base 5 of, well, recall that I said that the logarithm is the exponent. So what's our exponent here? 4. Okay. So our logarithm has to equal 4. What's left to fill in? The 625. 5 to the 4th equals 625. The log base 5 of 625 equals 4. Here we'd have 3 to the x equals 27. We'd say the log base 3 of 27 equals x. Remember, the exponent goes on the opposite side of the equal sign. The logarithm is the exponent. The logarithm equals the exponent. There's our base. 1/2 to the negative 4th equals y. Log base 1/2 of y equals negative 4. Now let's take these logarithms, rewrite them as exponentials. Log base 8 of 1 equals 0. That's the equivalent of saying 8 to the 0 equals 1. Log base 5 of 5 equals 1. 5 to the 1st equals 5. Log base 2 of 2 to the 4th equals 4. Our base 2, what's the exponent? 4 equals 2 to the 4th. Does 2 to the 4th equal 2 to the 4th? Yes, it does. All right, now let's get to evaluating them. Okay. I have the log base 2 of 8. I want to know, what does that equal? So we're looking for the exponent. What exponent are we looking for? We're wondering 2 to the what power equals 8? Well, we should recognize that as 2 to the 3rd equals 8. So we would say the log base 2 of 8 equals 3. Log base 8 of 8. 8 to the what power equals 8? Well, 8 to the 1st equals 8. So what does the log base 8 of 8 equal? 1. I'm not going to write this step anymore. I'll just write that as 1. Log base 8 of 8 equals 1. Let's see here. Log base 1/2 of 8. 1/2 to the what power equals 8? Well, I know that 1/2 to the 3rd would equal 1/8. What do I do with that fraction? I need to flip it, don't I? What in an exponent is going to flip the fraction? A negative. 1/2 to the negative third, negative flips the fraction, is going to give us 8. This logarithm is equal to negative 3. Log base 7 of 1. 7 to the what power equals 1? 7 to the 0 equals 1. There it is. A few other logarithms we might see. The common log. Remember that the common log, if there's not a number there, do you recall that that means that the base is 10? So if I want to evaluate the log of 100, that's the common log. I know I'm asking for the log base 10 of 100. So I ask myself, 10 to the what power equals 100? That would be 2. On our calculator, we have a log button. When I push that, that doesn't show, base doesn't show up there, does it? So that means this is the common log, base 10. If I were to type that into my calculator, the log of 100, I get 2. And shouldn't need a calculator for that one, right? Another log that we see is the natural log. Natural log of x, you will probably recall, that means it's log base e. Okay? So we don't write log base e, we just write it the natural log, remembering that our natural base is called e. So if I want to evaluate the natural log of 10, I would have to ask myself, e to the what power equals 10. Now, e is irrational. It's about 2.718. This is not something that I'm going to come up with in my head. I should be able to reason through, though. If e is between 2 and 3, what would I expect for the exponent to get to be 10? Well, 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. So 2 to the 3rd is 8. 2 to the 4th is 16. So between 3 and 4. Now e is actually closer to 3. And if I think about that, 3 squared would be 9. 3 to the 3rd would be 27. So that would say between 2 and 3. So I'm expecting between 2 and 4. 4 is probably going to be too big. Let's see what we get when we type this in my calculator. So underneath the log button, we should see that ln, which stands for natural log. So I'm going to go second natural log. Never mind. The natural log is under the log button. Forget the second thing. Should have looked at the calculator before I spoke to remind myself. I can just hit the natural log button, type in 10, and there it is. It's about 2.3. What we were expecting there. There it is. Whenever you're taking natural logs, just use a calculator to evaluate those. Really, really important. And I know it's been a while since we talked about inverses. We did that at the beginning of the semester. But there's an inverse relationship between logarithms and exponentials. What are some of the things that we remember about inverses? There's 3 important things to remember. One of them is that we switch the x's and y's. When we have inverse, we take the x and y, switch them. Doing that, number 2, creates a reflection over the line y equals x. Okay. Now, both of those pieces are going to be something that we're going to look at in a minute when I start looking at graphs. The third thing is that, I'll write it up here on the board, f of f inverse of x equals x. That they cancel each other out when I write them as a composition. Also, f inverse of f of x equals x. When I substitute one into the other, they will cancel out, leaving just x. This is what I want to use here to show that these really are inverses. I have y equals the log base 2 of x, and I have y equals 2 to the x. Let's look at a composition of the two of them. What happens when I put 2 to the x in here. I have the log base 2 of 2 to the x. Now, how do we evaluate logarithms again? Well, let me remind you. Let me just back up here a minute. Remember, we'd say 2 to the what power is 8? 8 to the what power is 8? Well, here I'm going to ask myself, 2 to the what power is 2 to the x? What's that question mark have to be? It has to be x. Notice when I substituted one into the other, they cancel each other out. Now, how about if I do it the other way? What if I take this and put it into the other function? 2 to the log base 2 of x. What happens here? 2 to the log base 2 of x. Well, if I think about log base 2 of x, if I want to evaluate that, that means 2 to the what equals x. Well, we have 2 to that what, that equals x, doesn't it? Okay. They are inverses. So, using that concept of inverses, let's come up with a graph of the log base 3 of x. Well, instead of coming up with a table of points for log base 3 of x, let's come up with a table of points for its inverse. The inverse of the log base 3 of x is 3 to the x. Log base 3, exponential base 3, inverses. So that's our exponential. Let me graph that. That's 3 to the x. Now, inverses, two things. What was that first thing? We take the x and y's and switch them. So if I want to graph x and the log base 3 of x, all I have to do is switch my x's and y's from its inverse. 1/9, -2. 1/3, -1. 1, 0, 3, 1, 9, 2. Now, let me graph that. I'll do that in red. Should have had my scale here go by threes. Oh well. We've got 1/9, -2. 1/9. Pretty much there. We've got 1/3, -1. We've got 1, 0. 3, 1. 9, 2 would be off. And the graph looks like that. Okay. Graphing logarithms I don't think is difficult. Just graph, come up with that table, graph its inverse, the exponential, take and switch them. Notice how these are reflections over the line y equals x. Let's graph another one. Log base 1/2 of x. What's the inverse of log base 1/2 of x? 1/2 to the x. Well, let's go through this. We know this would be exponential decay, wouldn't it? We've got -2, +4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. So we had -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. There's that exponential decay. Let's see if I can get through my points. Got it. That's 1/2 to the x. How do I graph its inverse? How do I graph the log base 1/2? Take our points and switch them. 4, -2, 2, -1, 1, 0, 1/2, 1, 1/4, 2. Four, -2. 2, -1. 1, 0. 1/2, 1. 1/4, 2. There it is. Now, again, they are reflections over the line y equals x. And we can see that that's a nice reflection. One other thing to think about here with these graphs is the asymptotes that we have. So in our first one here, 3 to the x, we had the x-axis as a horizontal asymptote. When I reflect that over the line y equals x, what do I end up with? I end up with that vertical asymptote, don't I? Do we see the same thing here? The exponential decay, x-axis, horizontal asymptote. What happens when I reflect that over the line y equals x? I get that vertical asymptote for the logarithms. So some things to point out here. Domains of logarithms. In both of these, we saw x's that could only be greater than 0. We had this vertical asymptote that we weren't ever going to get to x equals 0, and we're certainly not going to get to the other side. So our domain is 0 to infinity. Our range, what kind of y values are we having? We're having all the y values, from -infinity to +infinity. There it is. Now notice, these are the domain of range of exponentials just switched. Domain x's, range y's, inverses, switch. Knocked over my water bottle. Okay. I'm just switching the domain. 0 to infinity, that was the range of exponentials. Exponentials couldn't get down to 0. Well, switch that. The domain of logarithms, x's can't get to 0. Range, all real numbers. Now, if the base is greater than 1, that would be this one, like the log base of 3. We saw that the graph of our logarithm was increasing. If the base is between 0 and 1, that was like this one, log base 1/2, between 0 and 1, we can see that the graph of the logarithm is decreasing. Plot, okay, come up with that table, plot and graph the inverse, the exponential. Switch them to get the logarithm. Now, we know that we can do other things. What happens if I put a 2 in front? Vertically stretch it, right? If I go back and I put a 2 in front of this one, what do I have to do? I have to take this table, multiply the y values by 2, vertically stretch it. What would happen if I would put a -1 back there? We know it's going to move down 1. Take this table and move it down 1. We know all of the things. We know how to stretch. We know how to reflect. We know how to shift left and right, up and down. Do the same thing. Look at the parent function. Okay. Find its inverse. Find that parent function logarithm, and then do your transformations. So, with that, I'm out. Good luck as you work with your logarithms today. We'll pick this up later.